In this video, we're going to work through every question from the UKMT, the Andrew Jobbins Senior Kangaroo from 2022. That's a tough follow-on round to the Senior Maths Challenge. If you don't know how the challenges and the Kangaroos and the Olympiads work, I'll link a video in the description below where I go through all of the challenges talking about who they are for and how to qualify for the different rounds. Now, I've also put all of these questions into a totally free online course, and the best way to prepare would be to go and take that online course now, because that also has video hints for every question as well as the video solutions. But in this video here on YouTube, I'm going to put all of the video solutions so you can work through the entire paper here with me with those video solutions if you prefer. So we will get on with that now and start with question 1 of the Senior Kangaroo from 2022. The number x satisfies x squared minus 4x plus 2 equals 0, and we want to work out the value of x plus 2 over x. Now you might be tempted here to actually work out the value of x. This doesn't factorize, so you'd have to use the formula or complete the square or something like that. You could write down, x equals 4 plus or minus the square root of b squared minus 4ac, so that would be 16 minus 8 all over 2 times a. Using the quadratic formula, we'd get 4 plus or minus root 8 over 2, or 2 plus or minus root 2, because root 8 is 2 root 2, so I divide it by 2, it'd cancel out. And then you could take these individually, 2 plus root 2 or 2 minus root 2. It's implied in the question here that you would get the same thing either way, and you could work out 2 plus 2 over x using some surds. But actually there's meant to be an easier way of doing this, and when you've gone through all that, you might think, well hang on, this is question 1 of the Kangaroo, I'm not meant to be spending that much time on it. And in fact, if we ignore all of the usual thing was we would do with quadratics here and just divide this whole equation by x, right? I've got x squared minus 4x plus 2 equals 0. Dividing by x gives me x minus 4 plus 2 over x equals 0, and adding 4 to each side just gives me that x plus 2 over x is equal to 4, and so we get the answer of 4 right away there. And remember, in the Kangaroo all the answers are 3-digit numbers, so you would enter that in the paper as 004. I might not say that in every question if there's 1 or 2-digit answers, but that's something you should know when you're filling in your answer sheet. So this is a good example of a first question here where perhaps it's a bit mean because you can end up wasting a lot of time going down a different route here, but a good example of the earlier challenge questions where you'll probably get the answer whichever way you do this, but really we're trying to save ourselves time for later questions in this sort of one. It's quite a standard trick in this question that you will know very well if you've done a lot of maths challenges and taken my Go for Gold courses or practiced a lot of past papers. I've got some symmetry in the algebra here. So we've got Tom and John's ages sum to 23, so t plus j equals 23. John and Alex's sum to 24, and Tom and Alex sum to 25. So just call the ages t, j and a here. And if you add all of these three equations together, there will be 2 t's, 2 j's and 2 a's in all of them. So if I add them together, I just get 2 lots of t plus j plus a equals 23 plus 24 plus 25. So adding those together, we get 72. So it must be that t plus j plus a is a half of 72, which is 36. But of course I know t plus j is 23. So if I take that away from each side here, the t plus j, I'm subtracting this equation from this equation is what I mean, and then I get that a equals 13. Do the same with j and a here, subtract this one from this one, and I'm going to be just left with t equals 12, and the same for this one. Take t and a away, and I'm just left with j equals 11. We want the sum of the squares of their ages, so the answer to this question is 11 squared plus 12 squared plus 13 squared, and make sure you get this bit right and don't mess up the easy part here. Just add together 121, 144 and 169, and you will get the answer of 434. Okay, so Zia conducts a study of the number of coins each member of her club had in their pocket. To her surprise, no one has 0 coins. Exactly 7 people have 1 coin each. Everyone else has at least 2 coins. She drew a pie chart of her results, and to her surprise found each sector had an angle which was an integer 10 degrees larger than its immediate predecessor, and the smallest sector had an angle of 35 degrees. We want to know how many people there are in the club. So the smallest sector has 35 degrees, and it says each sector has an angle integer 10 degrees larger than its immediate predecessor. So the next one will be 45 degrees, then 55 degrees. And if I just keep working out the cumulative sum of these, so 35 plus 45, that gives me 80 here, plus 55 gives me 135, and then the next one is 65, that's going to take me to 200, and then 75 is 275, and then 85 takes me to 360. 360 degrees is the total for the circle, so we know these must be the angles in the pie chart then. And now the next step, I'm not sure if they intended it to be to require as much checking as perhaps it does here. We're going to use the fact that 7 people have only 1 coin each, and you know, it's easy just to do this and say, well, okay, let's just let the 7 people be the 35 degrees, and I think perhaps they meant to tell you that. Anyway, it's the only one that can be the 7 people. It's the only one that's a multiple of 7 here, so that means that if this is 7 people, then it's 5 degrees for 1 person, and you can check that if you make any of the other 7 degrees, you're going to end up with any of the 7 people, you're going to end up with one of the sectors representing a whole number of people. But I don't think they meant you to do too much checking there. I think we can just see that this one here, if I make this the 7 people, then all of the others are going to be whole numbers, and that's fine. So if 5 degrees is 1 person, then the total number of people in the club would be 360 over 5, which is 72 people. And so the answer is that there are 72 people in the club, or the answer for the kangaroo paper 072. Right, so let's draw a diagram for this one. We've got rectangles S1 and S2. S1 has vertices at 0, y, and y is going to be less than 4, so I'm going to put y somewhere here, so that's one point there at 0, y, and then also at xy, so let's make x a point here, and then also at x4 and 0, 4. Now I know that 4 is bigger than y, so 4 can be somewhere up here, and so there's my rectangle S1, and let's just label that. And then S2 has vertices at x0, so here, 9, 0, and again 9 is bigger than x, so that's to the right here, at 9y and at xy, so I can also draw in my rectangle here, S2, and we're told that these have an equal area. Well, the width of this rectangle is x and its height is 4 minus y, and for this rectangle S2 its width is 9 minus x and its height is y. The area of the rectangle is just base times height, so I've got x times 4 minus y equals y times 9 minus x. If we just multiply those out, we get 4x minus xy equals 9y minus xy, so the xy's cancel out, adding xy to each side, we get 4x equals 9y, and we want 360x over y, so if I just divide both sides by y here, I get 4x over y equals 9, so to get 360x over y, we just multiply both sides by 90, and so we get 360x over y equals 9 times 90, which is 810. They do a bit of manoeuvring in these questions to make sure the answers are 3-digit numbers at the end. You'll often find these approximations questions hard even with calculators, and you've got to do it without a calculator here, but still not too bad, I think. We've got a wall being painted and the area is 1,920 square meters, correct to the nearest 10. So our worst case scenario, if we're trying to cover this with a lot of paint, and we know we want to make sure we've got enough, is that 1,920 is actually 1,925, and that we've rounded down to this number, so that would be the largest that the wall could be. And each of the tins of paint, 18 square meters each, correct to the nearest integer, so the worst case scenario would be actually that all the tins had less paint than we thought, and so it would be 17.5 in each, and then the number of tins we would need would be 1,925 divided by 17.5. So if I multiply top and bottom by 10 here, just to get rid of the decimal, I would have this, and I notice that top and bottom are both multiples of 25 first. 175 is 7 times 25, and on the top, well, I've got 19250. We've got to divide that by 25. I mean, you could probably do this as a bit of a mental calculation if you're good at this sort of thing. If not, let's just do this bus stop method. I've got 7 with 17 left over, and then I've got 7 and 0, so I'm left with 770 here. And then I see I can cancel a factor of 7 as well, and we get that 110 tins of paint are needed. And then it's just a question of being careful here, because it says he needs to paint the wall completely and still have at least half a tin of paint left over for any minor repairs. So we're going to have to do one more, and then the answer is 111. Right, I've done my best here to draw a reasonable diagram of the setup here. A cube is dissected into 6 pyramids by connecting a given point in the interior of the cube, so that's this point here, with each vertex of the cube, so that each face is the base of a pyramid. So you can see like there's a pyramid on the top here, there's one from this side, there's one from the bottom, there's one going in from this way. When you put them all together, you get the whole cube. So the key here is, well, we know firstly that the volume of a pyramid is a third times the base area times the height of that pyramid. So let's just say the side length of the cube is x. So like for this top pyramid here, the one that's going from the top face downwards, its volume is going to be a third times x squared times whatever the distance is, the perpendicular height to this top face. So if we just call that distance h, then we get a third x squared h. But then the volume of the bottom pyramid here, right, well, that would also have x squared as the base, as its base area, so it would have a volume of 1/3 times x squared times x minus h, right, because it's a cube, so this side is also x, and this distance is x minus h if this one is h. What we notice in particular is that when I add these two volumes together, maybe I should call them V1 and V2 for the volume of this pyramid and the volume of this pyramid. Right, when I add those together, V1 plus V2 is, they've both got a third x squared, so it's a third x squared h plus a third x squared x minus h. So actually, well, this is just a third x squared h plus x minus h, so it's a third of x cubed because the h's cancel out here, right? So the point here is that this pyramid and this pyramid have a third of the total volume of the cube. This pyramid and this pyramid, by the same reasoning, will have exactly a third of the total volume of the cube, and similarly the ones like coming from this side, the front and the back sides, they will have a third of the volume of the pyramid as well. So what we need is 3 equal pairs when I combine those volumes, right? So if you look at the numbers we've got here, the only way to get pairs would be to do 200 plus 1400 equals 1600, and then we could do 500 plus 1100 is 1600 as well, and so the final pairing must be the 1000 with 600 to be another 1600, and so the answer here is 600, and the total volume of the cube is 3 lots of 1600 or 4800, but what we're asked for is the volume of the final pyramid, and so that is the answer there. Here we've got a positive inch to n, and it has exactly 6 distinct positive factors, including 1 and n, and the product of 5 of these is 6075. We want to know what's the value of the 6th factor. Well, you know that factors of numbers come in pairs unless it's a square number. Of course, if it was a square number, it would have an odd number of factors, so we know this number isn't square, but it's got 3 pairs of factors, right? So actually what happens is if I were to multiply all of those factor pairs together, right, I would get n times n times n, or n cubed. So I am looking for the product of these 5 numbers and one other number to be a cube number, and so let's have a look at 6075 and its prime factorization. I can see it's a multiple of 25 here, and it's going to be 25 times 243. Also, we've got the digit sum as a multiple of 9, so we know there's a multiple factor of 9 in there. In fact, you might also recognize 243 as 3 to the power of 5, or if you want, you can go 9 times 27 and then 3 times 3 and then 3 times 3 times 3. Really, however you get the prime factorization here, I don't mind, but it's 3 to the 5 times 5 squared. So I need to multiply by something else to get a cube number. Now, interesting bit of theory here is that cube numbers always have multiples of 3 in all of the powers of their prime factorizations, and it kind of makes sense, right? You know, if I do 2 times 5 squared times 11 to the 4, and then I cube it, I'm going to get 2 cubed times 5 to the 6 times 11 to the 12, right? So, all of these powers have been multiplied by 3 to get the cube, so I only get cube numbers when I've got multiple of 3 in all of the powers. You can think about how that applies for square numbers. They all have to be even, fourth powers, they all have to be multiples of 4, etc. So we need to make this, we need to multiply something to make this a cube number, so I need to make the powers multiples of 3, so the way to do that would be to multiply by 3 and by 5, and then I would get 3 to the 6 times 5 cubes, and that would work nicely. So it must be that this sixth factor is just 3 times 5, and the answer is 15, or 015 for the purpose of the Olympiad. And you can check that this does give you exactly 6 factors here, and in fact, obviously if I were to go, I could go larger as well, right? I mean, I could go to like 3 to the 6 times 5 to the 6, or 3 to the 9 times 5 to the 3, or 3 to the 90 times 5 to the 90 as well. But that wouldn't give us exactly 6 factors here, whereas with this number, it does do that. Because of course, n is now just the cube root of this number, which is 3 squared times 5, which is 45. So the factor pairs that we get are 1 and 45, 3 and 15, and 5 and 9, and it all works out nicely for the answer of 015, 15. Here we've got a right angle triangle ABC with its right angle at A, and the bisectors of the acute angles intersect at this point P. So the first challenge in this question, I suppose, is drawing this diagram, and I've just done the bisectors approximately here. The distance from P to the hypotenuse is the square root of 80,000, so the closest distance is going to be a perpendicular distance. So we know here that this length from here to here, let me just label that like that, is the square root of 80,000. And this can be quite a hard question to get your head into. It took me a long while to see what you had to do here, I think, actually, compared to some of the other questions. And but it's also, in a way, once you've done it, it is the obvious thing to do, I think, because we want to work out the distance P to A, and really the only way we're going to get that distance is by some sort of Pythagoras argument here. So I know that I'm going to need probably this line to be added, or perhaps this line here, and then I can do Pythagoras on one of these to get this distance here. And then once you have drawn that line in, I think it becomes a little bit clearer that I've got some congruent triangles here, right? In fact, in particular, this triangle and this triangle are congruent because we have this angle bisector, right? So the angle bisector means that it splits the angle exactly into 2. So these angles are going to be equal. I've also got right angles, so the other angles in these triangles are also going to be equal here, and they share this common side, so they must be congruent. And so in fact, this side length here is also the square root of 80,000. And then in these triangles up here, we've got exactly the same argument as well. Right, I've got an angle bisector, so these angles are equal. Again, I've got right angles here, and these angles must be equal. They share a common side, so they are congruent. So actually this side length here must also be the square root of 80,000. And then we can just apply Pythagoras' theorem to get the distance from P to A here. AP squared is going to be root 80,000 squared plus root 80,000 squared, so I get that AP here is the square root of 160,000, and the square root of 160,000 is 400. 400 times 400 is 160,000, and so that's the answer to this question. The distance from A to P is 400. Not the hardest one here, I think. We've got a 24-hour clock, and the time 16/11/22 corresponds to the date 16/11/22. The question is, when's that next going to happen, and when, and what's the square root of that number of seconds between the two? And actually, it's not too bad a question because it just happens the next day, right? I mean, 17/11/22 on the following day, we're going to have the same phenomenon occurring, and it's kind of clear that that's the next time that it happens, and that's exactly a whole day and 1 hour later, so it's 25 hours later. Now, I guess the slight trick here is that to work out the square root of s, it's the square root of the number of seconds, right? So the number of seconds would be 25 times 60 times 60. So we don't really want to go working out that number. We just want to go straight to the square root of it, because it's the square. I'm looking for the square root of 5 times 5 times 60 times 60, and of course that's just 5 times 60 then, so I get the answer of 300 for the solution to this question. If you've studied some of the further maths pure content about how the roots of equations relate to the coefficients in the equations, you may be able to shortcut some of what I'm going to do in this question, but I'm going to go about it assuming you don't know that stuff. But the basic idea is that if I've got an equation here, x squared plus ax plus b equals 0, and it's got real roots, so I should be able to factor it, and if I call those roots alpha and beta, it would factor as x minus alpha, x minus beta equals 0, right? So that factorization is equivalent to x squared plus ax plus b. But if I multiply this out, right, I get x squared minus alpha x minus beta x plus alpha beta equals 0. And for this first equation, that's going to correspond then to x squared plus ax plus b, right? So it must be that, so these are the same, so it must be that this a is equal to minus alpha minus beta, because that would be the coefficient of x here. If I just rewrite this, I could write this as, well, I suppose I could write it as minus alpha plus beta times x, perhaps would be a nice way of writing it, or minus alpha minus beta, and then b would be alpha times beta. So we're looking for something to do with the sum of the squares of the roots, and we can get that from this sort of expression by saying, well, okay, if I do minus alpha minus beta all squared, right, that's the same as minus alpha plus beta squared, so it's actually just the same as alpha plus beta squared, right? So I'm going to get alpha squared plus beta squared plus 2 alpha beta. So if I want to get to just the sum of the squares of the roots, alpha squared plus beta squared, I could do minus alpha minus beta squared, which would be all of this, and then I could subtract 2 alpha beta, and that would just give me alpha squared plus beta squared, right? So the idea here is that, well, then this corresponds to the a coefficient, and this corresponds to the b coefficient. So in fact, the sum of the squares of the roots here, alpha squared plus beta squared, is just a squared minus 2b. And we're told that it's the same in each of these equations, right? So in the roots for this one, we've got alpha squared minus 2b, sorry, a squared minus 2b, and in this one, the b and the a are switched around, so it would be exactly the same, but I'd get b squared minus 2a for the sum of the squares of the roots. So we're told that those expressions are equal, so we have a squared minus 2b equals b squared minus 2a, and then I suppose I've got a difference of two squares here, a squared minus b squared, and on the other side I've got 2b minus 2a, so I've got a plus b times a minus b is equal to 2 times b minus a on this side. And now if I divide both sides by a minus b, well, b minus a is just minus a minus b, so I'm going to get that a plus b equals minus 2, and then the expression that we want here is 500 plus 10a plus b, so that will be 500 plus 10 lots of minus 2, so 500 minus 20, and that gives us a final answer here of 480. Sorry to go all over the page there. But hopefully that makes sense. As I say, if you've studied the maths of how roots relate to the coefficients of equations, you'll be able to do this a lot more quickly, and you'll have thought about this before, but it is possible to do this as a sort of problem-solving exercise just in this question without knowing that as well, I guess. So there's the answer anyway, 480. Here we're told that we've got a quadrilateral that contains an inscribed circle. It tells us that that means that the circle is tangent to each of the four sides of the quadrilateral, and I've just drawn a picture of what that might look like here. And I'm doing it in general, I'm not making any assumptions that anything's regular here, it might not be. So the ratio of the perimeter of the quadrilateral to that of the circle is 4 to 3. So let's just say the radius of the circle is r, then we know that the circumference is equal to 2 pi r. So the perimeter of the quadrilateral then will just be 4/3 of 2 pi r, or 8/3 of pi r. Now, if you want to at this point, you could just take r equals some multiple of 3. The radius here really can't be important to this question. We've just got ratios at the beginning and at the end here, so if you're confident that that's a fine thing to do, you could do that. It's not too hard just to work in general here, so I'm going to carry on working in general here. Now, the hard part here then is to work out, well, okay, how do I get an expression for the area of this quadrilateral? And very often in circles questions, we'd want to put the centre of the circle in and look for radii that might be useful. Now here I'm going to add in some lines that are not radii first, that just link the centre of the circle to the corners of the quadrilateral here. And what we're going to notice is that I end up with these 4 triangles, and all of them have perpendicular height that are the radii, because we've got this circle theorem that says the radius at a tangent meets right angles, right? So I've got a radius and a tangent, so it must be a right angle here. So this radius here is the perpendicular height of this triangle, where this length here would be the base, right? And similarly, I can put in radii here, here, and here to each of those tangents, right? And then those other 3 triangles also have the same property, right? I've got the radius here, here, and here, and if this is length B, and this is length C, and this is length D, right, then I can work out the area of the quadrilateral by adding together those 4 triangles. They're all half base times height, right? So it's a half AR plus a half BR plus a half CR plus a half DR. Well, that's just a half A plus B plus C plus D times R. But the perimeter is A plus B plus C plus D of the quadrilateral, right? Whatever it's in down here. So this is a half times 8/3 pi R and another R. So I've got 4/3 pi R squared. Well, that's 4/3 of the area of the circle, right? Because the area of the circle is just pi R squared. So actually the ratio of the area of this quadrilateral to the area of the circle is also 4:3. So A is 4 and B is 3. And so we get an answer to this question that 100A plus 49B is 100 times 4 plus 3 times 49. So that is 547, and that would be the answer to this question. So quite a tricky one, I think, but quite a nice, satisfying solution once we get there. We've got 5 cards here labelled with different numbers. On the reverse, each of them have positive integers A, B, C, D, and E, and we're told some relationship between these values. Gina picks up a card, and she picks up the one that has the largest integer on the reverse, and we want to know what number is on the front of Gina's card. Now, it took me a while to realise that these numbers 101, 102, etc. are not really relevant to the question. They're just a way of picking out one of the answers. So this is kind of a multiple choice question. The closest you get in a kangaroo question, we know the answer is going to be one of these 5 numbers. And really, it's just a question of saying, well, if these are positive integers, which of A, B, C, D, and E is going to be the largest, right? So let's go through one at a time. Right? I know A plus 2 equals B minus 2, and so that means that B is equal to A plus 4. So these are all positive integers, and so certainly it must be that B is larger than A, and I suppose I also know at this point, A has to be at least 1, so B is also larger than 5, which may be useful at some point. We'll see. So now let's compare. We've got B is my candidate for the largest at the moment, so I'm going to compare it to C. Well, I've got B minus 2 equals 2C, and so B equals 2 times C plus 2. Well, if C is a positive integer, then this means that B is going to be larger than C for sure, because I'm doubling C and adding 2. So B is bigger than C. And now let's think about E here next, I think. So let's say B minus 2 equals E squared. So B equals 2 plus E squared. Now, I suppose B is clearly going to be greater than E as well then, because when I square the number E, it's going to get larger, unless it's 1, I suppose. I mean, we know that B is bigger than 5, so E can't be 1 here anyway. So either way, E squared is going to be bigger than E, and that means that B is also going to have to be bigger than E as well. So I've just got D to compare to. We've got B minus 2 equals D over 2, and so this gives me that D equals 2 times B minus 2 here, and I suppose if B was 1 here, D might be smaller than B, but otherwise, if B is 2, I suppose they'd be equal, but if B is 3 or bigger, and we know B is bigger than 5, if B is 3 or bigger, then D is going to have to be bigger than 2B minus 2, and so it must be actually that D is greater than B, and so the answer here is that D is the largest one, and these are meant to just be in order A, B, C, DE. So the answer to this question is 104. I think slightly confusingly worded in sort of, I think I would have written that this one is definitely A, B, C, D, and E in that order somehow. I suppose it does say that. It's clear if you read it carefully, but I did have to read it a couple of times just to convince myself that was true. Anyway, the correct answer is 104, so well done if you got that. Well, we've got a sequence given by x1 is 2, and then we've got the rule to go from one term to the next. And we've really just got to very carefully follow this through, right? So x2, right, for x2 we've got n equals 1, so x1 is 2, so it's 2 to the power of 2, and then I've got 32 to the 1 minus 1, so 32 to the 0. So that's just 4 over 1, which is equal to 4. So for x3, I've got n equals 2, so I've got x2 to the power of x2 divided by 32 to the 2 minus 1, so that's 4 to the power of 4 over 32. And at this point, you might want to keep things as powers of 2, so this is 2 squared to the 4, and 32 is 2 to the power of 5, so this is 2 to the 8 over 2 to the 5, which is 2 cubed, or you could work out that it was 8 in another way if you wanted to just do 4 to the 4 is 256 or something like that. That would also work. But for x to the 4, so x, not x to the 4, but x4, the fourth term in the sequence, so this time I've got x3 to the x3 divided by 32 to the 3 minus 1. So now I've got 2 cubed to the 2 cubed, which I'm going to write as 2 cubed to the 8. And on the bottom I've got 32, which is 2 to the 5 squared. And so I've got 2 to the 24 over 2 to the 10. So that's 2 to the 14. So at the last stage here, working powers of 2 makes life a lot easier. So I now want to work out x to the 4 over 128. Well, that's 2 to the 14 over 2 to the 7, and that gives me 2 to the 14 minus 7, which is also 2 to the 7, which is 128. And so the answer here is 128. Probability doesn't come up that much in the maths challenges, but here it is in the Senior Kangaroo. We've got a class of pupils each wearing either a red tie or a green tie, and there are 2 more pupils wearing green ties than wearing red ties. So let's write G equals R plus 2, where G and R are the numbers of pupils wearing green and red ties respectively. So the total number of pupils in the class would be R plus G, which is going to be 2R plus 2. We're going to pick 2 pupils at random, so we've got a kind of classic tree diagram situation here where I can have red and green on the first layer and also on the second layer here. So if we write down the probabilities, well, to begin with, we've got the probability of picking someone with a red tie being R over 2R plus 2, and of a green tie being R plus 2 over 2R plus 2. Once I pick someone who's wearing a red tie, there's only R minus 1 people with red ties left, and only 2R plus 1 left in total, but there are still R plus 2 with green ties out of 2R plus 1 in total. Whereas if I pick someone with a green tie first, there would be all the R pupils with red ties left, and 2R plus 1 here, and on this final branch we would have 1 fewer with a green tie, so just R plus 1 over 2R plus 1. So I can just translate this into algebra now. The probability of selecting 2 pupils of different tie colours, so that's going to be red green and green red. So the probability of red green is going to be R over 2R plus 2 multiplied by R plus 2 over 2R plus 1, right? That's this branch in the tree diagram, and then I add that to R plus 2 times R over 2R plus 2 times 2R plus 1, and actually if you notice that's exactly the same, it's got exactly the same stuff here. And if you're more experienced with tree diagrams, you might have known that was going to happen already, and you could have just written down that, we've got 2 times this whole fraction for this probability. That's the probability of selecting 2 pupils of a different tie colour. And we're told that that's triple the probability of selecting 2 pupils who both wear red ties, so that's 3 times this times this, and so that's R times R minus 1 over 2R plus 2 times 2R plus 1. And again, with some experience, you might have known here that all the denominators were ultimately going to cancel out, but fine to just write it down this way as well. So if I multiply both sides by the denominators, right, I'm going to clear out all of this, and I'm just going to be left with 2r r plus 2 equals 3r times r minus 1. So now multiplying out, I get 2r squared plus 4r equals 3r squared minus 3r. So moving everything to the right hand side, putting equal to 0, I've got 0 equals r squared minus 7r, so 0 equals r times r minus 7, so that gives me r is equal to 0 or 7, but we're told that r is greater than 0, so it must be that number of people wearing red ties is equal to 7, so I want to work out r cubed plus r squared plus r, so we just need 7 cubed plus 7 squared plus 7, so that's 343 plus 49 plus 7, 343 plus 7 is 350, so plus 49 gives us a final answer here of 399. In this question I've just made a slightly bigger copy of the picture to work on, but we're told in this picture the square has a perimeter of 40, and we want to know what the perimeter of the larger equilateral triangle is, basically in this form, and then we will do some manipulation of the values to get an answer suitable for entering in the kangaroo. But basically the question is, what's the perimeter of the large equilateral triangle? So the perimeter of the square being 40 means that each of its side lengths is 10 all the way around, and what I'm going to do is add an extra line down here, right? Because what I'm going to be able to do now is say, well, I know this angle here is 60 because it's an equilateral triangle, so if I've made this a right angle, then and this is 30, 60, 90 degree triangle, and I can work out the perimeter of the large equilateral triangle then by basically working out what this length is, and then I can sort of add it to this one. Well, this one's going to be the same as this one, and then I can get this top equilateral triangle through knowing what this length is, and we'll be able to do all of that just by working out working with this triangle here. So you do need to know for the senior challenges that sine of 30 equals a half, and that's also equal to cos of 60, and that sine of 60 equals root 3 over 2, which is the same as cos of 30, and that tan of 30 is 1 over root 3, and that tan of 60 equals root 3. I say you need to know it, you don't really need to memorize it, I suppose, as long as you know that you can get them all by looking at an equilateral triangle of side length 2 here, and then, you know, just saying, well, that's 30 and that's 60, sorry, that's a bit small, and you can just deduce all of those facts from knowing that triangle. But we're going to use that here, right, because let's just call this side, this length here, x, right? Well, I know that this is 10, right? So I've got that. So let's use the angle of 30 here, right? And I've got the adjacent side and the hypotenuse. So we've got cos of 30 is equal to 10 over x, and rearranging that, then that gives me that x is equal to 10 over cos 30. So that's 10 divided by root 3 over 2, or 10 times 2 over root 3. So that gives me 20 over root 3 here. So that is the value of x, 20 over root 3. And similarly, this base here, let's just call that y for now. So I'm going to have sine of 30 is equal to, well, actually let's use tan with the original value. So tan of 30 equals y over 10. So y is equal to 10 tan of 30. So that gives me that y is equal to 10 times 1 over root 3, or 10 over root 3. So if we call this z, then z is going to be 10 minus y, so that's 10 minus 10 over root 3. And so of course this, this length here is also z, and this length here is also z, because I'm going to have a little equilateral triangle at the top. Now, lots of ways you can add all these pieces together. Now I've just got to add together all the bits of the equilateral triangle. I think perhaps the easier thing to do now is to say, well, look, I know x and z together, right? So I've got what I'm looking for is 3 lots of the long length of the equilateral triangle. So that's 3 lots of x plus z, basically. So that's 3 times 20 over root 3 plus 10 minus 10 over root 3. So that is 3 times 10, and then 3 times 10 over root 3, just combining these two together, and 3 times 10 over root 3 gives me, well, 3 divided by root 3 is root 3, so that's 30 plus 10 root 3. So I've got everything I need to do the answer now, right? I've got 30 plus 10 root 3, so it must be that A is 30, B is 10, and P is 3. So we can do 7 times 30 plus 5 times 10 plus 3 times 3, and that gives me 210 plus 50 plus 9 for a final answer of 269. Got a bit of a logic puzzle here then. On the island of friends and foes, either the citizens are all friends or foes. Now the friends always tell the truth, so I'm just going to represent them by T's when I write them down, and the foes with F's, because then we have different letters, so we're not just F and F. I've got 7 citizens sitting in a circle, so let's just represent those by dots here. And firstly, let's think, well, could they all be foes? Well, if they were all foes, then actually at least someone's going to be telling the truth, because they are sitting between 2 foes, but foes don't tell the truth, so that's not possible. We can never have 3 foes sitting next to each other, basically. So there must be at least someone telling the truth, at least some friend, and because they're telling the truth, we know there's a foe either side of them. Now if we consider the next person here, well, actually we don't know at this point whether they're telling the truth or not. So I've got 2 cases that I can consider here. Let's have this one drawn out separately. So I've got the same situation, but this next person is a foe. Now let's just think about the different possibilities. So in this one, I can't have 3 foes next to each other, so this one next person must be telling the truth, and then this one must be a foe because the person telling the truth has 2 foes either side of them. And again, I can't have 3 foes together like this, so this person must be telling the truth. And so here there are 3 people in the circle telling the truth. And at this point, we kind of know that the answer to the question must be 003, because we found a consistent way of doing it. So it must be that this other way also would give us the same answer, but we can double check here, right? So this person telling the truth must have a foe next to them. And then over here, I can't have 2 more foes because then they would be telling the truth. There'd be sets of 3 next to each other. So it must be either here that it could be like this is one possibility, or it could be that there's these 2 the other way around. But either way, there would be 3 friends in total. And so we can see that the answer here is 003. So I think this question is a little bit harder than it looks. I want to know what the smallest 3-digit positive integer, which can be written in the form pq²r is, where p, q, and r are all distinct primes. So there's kind of a lot of cases that we can consider here, and we just need to sort of organise our thoughts somehow. So I'm going to do that by thinking about q first, because q is kind of the sort of special one here, and making q bigger makes the number bigger to begin with, right? So let's think about the cases where q equals 2 to begin with. So that means that q² is equal to 4. So the numbers that I'm going to be looking for are multiples of 4. So I need a 3-digit integer, so it's going to be at least 100. So if I start with 100, and I can think about, well, what would that mean for p and r, right? So p times r then would be 100 divided by 4, which would be 25, and I can't have that as a product of 2 distinct primes. So I'm looking for something here that is a product of 2 distinct primes, and in particular also they can't be 2, right? So if I did like 104, I could think, 26 is 2 times 13, but I've used 2 already, so actually I can't do that one. And in fact I could immediately rule out all of the every other one here, because I'm going to get a factor of 2 in them, right? So the next one I might check is 108, but then I don't really need to check 112 because that's going to be 28. It's going to have a factor of 2 in it again. So I can just actually go straight to 116 here, 124, 132, and so on. All right, so actually this one would be 29, 31, and 33. Well, thinking about like the first one that I can split into a pair of prime factors here is actually 33. That's 3 times 11. So that would work here with q equals 2, p equals 3, say, and r equals 11. Those 2 could be the other way around. So we can do 132. Another question is, can we do any better than that? Well, I could try and play the same game with q equals 3. So q² is equal to 9. Now the first one I'm going to check here is 108. That's the first multiple of 9 bigger than 100. Okay, I've already checked that doesn't work, but let's just follow through the same logic here, right? So 108 divided by 9 would be 12, so I would need p times r to be 2 primes multiplied together to give 12. Not going to work, as we've already seen. So then I could try 117, and then I'd have 13, and that's prime itself, so I can't write that as 2 primes. And then the next one is 126, so that would be 14. That is 2 times 7, so that gives me a possibility here that Q is 3, P is 2, and R is 7, so that would seem to work. What about, now can we do any better with larger values of Q? Well, if Q is 5, then that means Q squared is 25, and so PR, I'm going to be left with 4 for 100 is the first one, right? So PR is 4. That doesn't work. And now the next one takes me to 125. Then then P times R would have to be 5, and that can't work. And if I go beyond that, I'm gonna be only looking for things that are worse than my best current answer of 126. Similarly, if I just check like Q equals 7, well, the first multiple of 49 that's bigger than 100 is 147, so that's immediately bigger than something we've already found, so I don't need to investigate that further. Q equals 11 then gives me Q squared is 121, so clearly that doesn't work, and then anything else is going to be bigger. Larger primes, their squares are already going to be bigger than 126, so I don't need to check any further. So perhaps not. It seemed like there might have been quite a lot of work at the beginning, and there was actually quite a lot of checking there, but we can see by this logic that 126 is the answer to this question, and that must be the smallest 3-digit positive integer that can be written in this form. Not the most satisfying question, I don't think, but perhaps a good example of what we might call brute force, where you just do a lot of work and realise that actually a lot of work doesn't necessarily take you that long, depending what you have to do. We do have a bit of a challenge to start, I suppose. I've got this number, and it's got n prime factors, not necessarily distinct. So you might just have to think through, what does that mean, right? So actually, if I've got a number like 2 squared times 3 times 7 to the 4, this is going to count as having 7 prime factors. So it's not necessarily distinct, wouldn't be written otherwise. So it's 2 times 2 times 3 times 7 times 7 times 7 times 7, so all of those are counted, including the repetitions. So if we just think about this number for a second, well, we've got 20 factorial over 16 factorial, so that would have 1 up to 20 multiplied together, and on the bottom I'd have 1 up to 16. So all the ones up to 16 would cancel, and I'd just be left with 17 times 18 times 19 times 20 on the top. And then similarly for 22 factorial over 11 factorial, let me write that down here. Right, I'm going to end up with 22 times 21 times 20 times 19 times 18 times 17 times 16 times 15 times 14 times 13 times 12. And at this point, there's so much written down, you might think for a maths challenge question you've done something wrong. I sort of thought that as I was doing this, perhaps there's a better way, but I can't see a better way of doing it. Because now I've got this number is just all of this stuff times all of this stuff, so I can just count the prime factors pretty quickly, right? 17 is just 17, 18 is 3 squared times 2, so it's 3, it's got a 3, a 3 and a 2, 19 is just 19, 20 is 4 times 5, so it's got a 2, a 2 and a 5, so up here I've got 1, 2, 3, 4, 5, 6, 7, 8 factors from those numbers, and I just do the same here. I've got 2 and 11, 21 is 7 and 3, 20 again is 2 squared times 5, 19 is just 19, 18 is 3 squared times 2, and 17 is just 17, 16 is has got 4 factors of 2, so actually I'm just going to count the lines later. I think 15 is 3 times 5, 14 is 2 times 7, 13 is just 13, and 12 here is just 3 times 4, so that's 3 times 2 times 2. And if I count how many lines I've drawn, that should be how many factors there are here. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and I think I've got that right. So the whole prime factorization would be all of these multiplied together, so the total number would be that n is 24 plus 8, which is 32. And then for the answer to this question, I need to do n times n minus 2. So that's going to be 32 times 30, which gives us 960 as the final answer there. So perhaps there's a fast way of doing it. It feels like there should have been something clever with n times n minus 2 or something, but Anyway, the point here is I think I haven't taken that long to do this question, and so this brute force method, although it was a bit awkward, didn't really take that long, especially if I wasn't saying it. I'd have done that a lot more quickly. So if you see a way to do a problem, sometimes you're better off not thinking about it too much further, just getting on with it. If you can see you can do it in a minute or so, get the answer, move on, think about it again later perhaps. But as I say, I think that may well be the best way to do this question anyway. How many real number solutions are there to this equation? Looks a bit complicated. I've got a quadratic to a quadratic equals 1. Actually, I did a similar question on my YouTube channel in summer 2023, if you want to go and look at the Mathsaurus YouTube channel for another one of these later. So there are a few cases to consider here. So to get something equals 1 here with this powers, it's either going to have to be, let's call them 3 cases, right? So case A, I'm going to do 1 to the power of anything, right? So 1 to the power of any value would work here. I could also have minus 1 to the power of an even power, or I could also have something that is not 0 raised to a 0 power, right? So something like 3 to the 0 or 5 to the 0. So I'm going to look out for these 3 different cases. So in case A, I need x squared minus 8x plus 15 to be equal to 1. So to get that to work, I just solve this equation, then x squared minus 8x plus 14 equals 0. And I don't really need to solve it properly at this point. I can just say, well, I can see the discriminant is positive here, if you like, or you could start doing the quadratic formula and see that you're going to get at some point 64 minus 4 times 14 is 56. So I get something that's got 2 real roots here. That's the point, and I don't really need to work out that any further. Whatever values of x are here, it doesn't matter what I put in here. When I substitute them into here, I'm going to get something that is a number, so I'm going to end up with 1. So this case gives me 2 possibilities. Now for minus 1 to an even power, right, well this time I want x squared minus 8x plus 15 equals minus 1, so that would give me x squared minus 8x plus 16 equals 0. That's x minus 4 squared equals 0. So for this one, I just get the one possibility, x equals 4, which would make this part minus 1, but I do just need to double check whether it makes this expression even. Well, 4 to the power of 5 minus 5 times 4 cubed plus 4 times 4, well, this is an even number minus an even number plus an even number, so it is going to be even, and I don't need to work out the number explicitly to know that, so I get one solution from this case. And now in this last one, I need something that's not 0 raised to the power of 0. So for this final case, I need to think about x to the 5 minus 5x cubed plus 4x equals 0. So I can factorize this as x times x to the 4 minus 5x squared plus 4 equals 0. Now I've got a disguised quadratic, right? So if I put y equals x squared, then I'm going to get this would be y squared minus 5y plus 4. Cover this sort of thing a lot more in my online course, Get Ready for A-Level Maths, by the way, which is great for sort of year 12 students at the start of A-Level. Covers a lot of things that could be relevant for A-Level Maths and a bit for the Kangaroo, with some harder Maths Challenge style problems in there as well. So have a look at that if you're interested. Anyway, back to this problem. So I've got this disguised quadratic. So this one, you see, factorizes as y minus 4 times y minus 1. So that basically means that this factorizes as x squared minus 4 times x squared minus 1 equals 0. But now I've got a difference of 2 squares in both of these brackets. So I've got x minus 2, x plus 2 times x plus 1 times x minus 1 all equals 0. So I get different possibilities, x equals 0, 1, minus 1, 2, or minus 2. And we just need to double check that none of these would give us 0 when I put them in here, and it's easy to check that you won't get 0 with any of those values. So it won't be 0 to the 0, so I get 5 different cases here, and that means the answer to this question, the total number of solutions is 2 plus 1 plus 5, and so the final answer here is 8. And we would enter that in the Kangaroo as 008. So we've reached the last question of the Kangaroo. They often put something like this in, bit of a time filler, perhaps something you might take away if you don't have time in the Kangaroo. I don't think many people have time to do all the questions and get to this one, but they're quite fun ones to have a go at. So let's try it here. Really with these cross numbers, it's finding a way in and finding sort of the most restrictive option. So I sort of start reading through this. Well, 2 less than a prime. Okay, two digit. There's quite a lot of 2-digit primes. I don't really want to start there. Exactly 100 more than its largest proper factor. That seems a bit hard to think about. A multiple of 13, well, starts to feel a bit more promising. Perhaps I can write down the multiples of 13 pretty quickly here that are the right size here. 2-digit numbers for the cross number. So let's just have those in case that might be useful later. Now, it looks a bit more promising now. The 4th power, right, well, there's only 2 4th powers that are 2-digit numbers. That's 2 to the power of 4, which is 16, and 3 to the power of 4, which is 81. So that might be a good place to start. Cube numbers, I've got 3-digit cubes. Again, not too many of those. You had a great advantage if you can just write these down quickly. 5 cubed, 6 cubed, 7 cubed, 8 cubed, and 9 cubed. There will be the only options for that one. And then not prime, not square, not even. Well, you know, it's going to be a lot of examples there for a 2-digit number, I think, so we're not going to think about that one just yet. So the 4th power seems like the best place to start. So let's say maybe let's try and see if it was 16. Now 2 less than a prime, well, that could work. Exactly 100 more than its largest proper factor here. This one I think can't work, right? Because it's going to have to be 600 and something, and it's going to say, and then it's going to have a proper factor that's 500 and something. Well, it would have to be 500 and something times at least 2, so then it just doesn't work, right? So actually this 16 case doesn't work. Whereas if I put in 81, well, a number that's 100 and something could have a proper, you know, if it was like 102 or something, I can have a factor that's 2, right? Now that's not the largest proper factor in this case, but it's the sort of thing that might work out. So we can definitely rule out the 16 here and go with 81. Now we look at 1 across, I think, and say, well, 2 less than a prime. Now this really does narrow down a little bit. Let's think about 2-digit numbers in the 80s that might be prime. Well, I've just got to think about odd numbers, and let's work out which ones are prime and which ones are not. I suppose I might want 91. Actually, I don't need to consider 81 because 2 less than it would be in the 70s. Obviously, it's not prime anyway. So remember, to check 2-digit numbers are prime, we just need to know if they're multiples of 2, 3, and 5. I've got rid of the even numbers already. Let's get rid of the multiples of 2, 3, 5, and 7, because I just need to check the square number, the prime numbers less than the square root. So 8 plus 7 is 15, so that one will be a multiple of 3, but none of the others are. And 91 is 7 times 13, so that one is not prime. So I've either got 83 or 89 to check here. So the only options for 2 less than a prime are 81 and 87 then. Now if I follow this through, let's imagine it was 81, then the cube number would be 125, the multiple of 13 would be 52, but now 4 down has to be not even, so it would actually be even here. So I can't do 81, actually I have to do 87, and then my cube number can be 729, my multiple of 13 can be 91, and now I need not prime, not square, and not even for this one. So what could it be? Well, it can't be 11 because that's prime. 21 is not square and not even, but now the largest factor of 122 is 61, so that's not 100 less than it, so it can't be 21, so we can rule that one out. 31, well, again, 123 here has 3 as a factor, so 41 is going to be a proper factor, so it's not going to be 100 more than its largest proper factor, so we can rule that one out. 41, again, because this would be even, that's not going to work for the proper factor, it's going to have 62 as a proper factor. 51 looks good because that's not prime, not square, and not even, and then 125 is 5 cubed, so its largest proper factor is 25, which is 100 less than 125, and so we have there found the answer. And now once I've got something that's consistent that works, I don't have to keep checking whether 61, 71, etc. might work. You can go through and check that they don't work as well if you want to, but for the purpose of this question, I've solved the cross number, and now I just need to work out a half of t, where t is the sum of all of the answers here. So if I just add together 87, 125, 91, 81, 729, 1,051. Okay, I've done this earlier, but you can just add these up. You get 1,164. So I need to divide that by 2, and you will get 582. And so that will be the answer to the final question here of the Senior Kangaroo from 2022. So well done if you got that right. You get an hour for the real kangaroo, but if you've done these questions in a couple of hours or got anywhere near to getting some of them right, then you're doing well. It's meant to be a really tough competition. So I hope that's been useful, and good luck if you're taking it this year.